let's continue on with Lewis structures. So I'm recording this also.
That's a good question.
Yes.
There's KMOL. What does that stand for?
KMOL? Actually, I'm not sure. Where did you see that? In the homework? What problem number is that? Well, I'll come back to it. We'll come back to it. I'll take a look and see. KMOL could mean.
There were units given, I think it was kilograms or something like that.
All right, I'll have to look for it too. Yeah. All right, since there's still, I was going to do one thing here. Let's talk about multiple bonds. Sometimes a single bond is not enough to get an octet. And so there's examples of multiple bonds. So O2 was one where we would have to do a multiple bond in order to get an octet, because we have two oxygens, and oxygen has 6 valence electrons, so that's 2 times 6. So this is going to give us a total of 12 electrons. And we only have two atoms, so we have to link the two atoms together like this. And then what we do is we complete the octet to the terminal atoms. And so oxygen would get 3 additional lone pairs to complete the octet on each side. And now we have an octet on each of these, but when we count the electrons, let's go ahead and count. How many electrons do you guys count there? 14? Total number of electrons. Still 14?
14, right? The line in the middle says 14, right?
Yeah. 1, 2, 3, 4, 5, 6. Yeah, 7, 8, 9, 10, 11, 12, 13, 14. That's correct. 14 electrons, but do we have 14 electrons here? We don't have 14 electrons. And so what that means is I have to erase 2 electrons. So which 2 electrons should I erase?
Anyway.
Well, anywhere, right. Probably to be fair, since the 2 oxygens are equivalent, let's go ahead and remove 1 from each oxygen. So if I remove 1 from each oxygen, do I still have an octet? No, I'm not going to have an octet, because when I count, let's count the total number around this oxygen.
7.
It's 7. That's 7 electrons. And then on this oxygen, it's also 7 electrons. So the number one thing we look for in Lewis structure is the octet rule being satisfied. And so it turns out there is a way to make an octet in this case. And the way we can make an octet is by sharing those 2 lone electrons in the bond. And so if we share these here, then we end up with only 2 lone pairs on each oxygen. And we converted those electrons into an additional bonding pair. And so we end up with this structure.
I'm going to say I've never seen the one above, but I've always seen the one that's in the middle. That's cool.
Yeah, this one, right?
Yeah.
It turns out I need to put a little asterisk here, because this Lewis structure doesn't accurately describe oxygen. In other words, this is one of the limitations of valence bond theory, this thing we're using for this. We really should use what theory? Hmm?
The quantum?
Yeah, we need to use the full quantum, and that's MO theory. This is an exception here. Well, MO theory is used for all, but this one is where we see some big deviations from experimental and theoretical. MO theory required for O2 to properly describe. So that's an example. Another example of where we would use multiple bonds is for something like nitrogen. And so for nitrogen, we have 2 nitrogen atoms, and each nitrogen has 5 valence electrons. And so that's just 2 times 5, which is going to give us 10 electrons here. And so if we do this, we do something like this, and then we try to complete the octets, but it doesn't quite work out because, again, we're going to end up with 14 electrons here, which is too many. We have to get rid of 4 electrons in this. So if we get rid of 4 electrons, we'll just take 2 electrons from each nitrogen. And so we end up with this structure. But this structure here, does it have an octet?
No.
No. And so what I'm going to do is, I don't want to generate free radicals because free radicals are unstable, that is unpaired electrons. So what I'm going to do is I'm just going to take one of these pairs and then throw it into the bond here. It's a little asymmetric in that way that it affects the right-hand nitrogen more than the left-hand nitrogen. So we end up with this structure here. Did this fix it? So it looks like, you know, it fixed it for the left-hand nitrogen,
Not for the right hand.
but not for the right-hand. So left-hand nitrogen has 8 electrons if we count the total in the circle. But the other nitrogen has how many?
6.
6 electrons. That's not enough.
Did you put like 3 bonds
What's that?
Did you put like 3 bonds in between?
Yeah, exactly. So that's what we're going to do. We're going to take this additional lone pair and then drop it into the bond. So both nitrogens will contribute a lone pair and convert it into a bonding pair. Okay, now let's check the octet. Is the octet rule satisfied at this
Yes.
point? Yeah. Okay, yeah, because this has 8 electrons, and this would have 8 electrons. Now, not only do we have to satisfy the octet rule, we also have to worry about formal charge. When we're doing Lewis structures, we look at octet first, and then formal charge second. What we want to do is we want to minimize the magnitude of the formal charge. In other words, we want to keep the formal charges as small as possible. And so in this particular case here, with this oxygen, we want to do the formal charge for these. And so when I do formal charge based on the Lewis structure, this is how I do it. I divide the bonding electrons in half, like this. And so that means out of the 2 in this top bond, only 1 goes to the left, 1 goes to the right, and then the 2 on the bottom bond, 1 goes to the left, 1 goes to the right. And then what we do is we count how many electrons now this oxygen has. Okay, when we do octets, we look at the total number of surroundings. So when we count or divide the electrons up, when we're doing octets, we share it completely. However, when we do formal charge, we split them evenly. And so what's the count? How many electrons does this oxygen on the left have now?
6.
That's 6 electrons. How many did it contribute?
2.
No, contribute totally to the Lewis structure. This would be the contribution of each oxygen.
6.
Yeah. It contributed 6 and it ends up with 6. So did it gain or lose? No. And so what we say is if it didn't gain or lose, it has 0 formal charge. Okay, this other oxygen, how many electrons does this one have? 6. And therefore, it gave 6 initially. We look at how many it gave initially and how many it ends up with. In other words, this is like, you know, people in California complain about, you know, sending federal taxes because, you know, you give this amount of money, but California doesn't get back that amount of money. And so California gives much more money to the federal tax system than it gets back in services. Whereas some other states, they give less, you know, it's just how they distribute the income from the taxes and end up with more. And so that happens with the Lewis structure. Sometimes oxygen will give 6 but ends up with fewer. Sometimes oxygen will give 6 and ends up with more in the actual Lewis structure. And that's what formal charge tells us. Tell me what the formal charges of nitrogen are. They're both 0, exactly. Because each nitrogen, when we look at the nitrogen and divide up the electrons, both nitrogens end up with 5. You know, half of these bonding ones, and then it has 2 that belong solely to it. And so this ends up being 5 electrons. And how many did it contribute? 5. And the same thing here. So it broke even. When it breaks even, we call it 0 formal charge. Usually we don't show 0 formal charges. 0 formal charges are good. We like 0 formal charges because however, then we don't always have to have 0 formal charge. So let's look at some other structures with non-0 formal charges. And that's going to make them less stable. So one of these will be, let's see. PClO4 plus, this one. This one's called tetrachlorophosphonium ion. It's not one of those ones, but it's a polyatomic cation. Let's give that one a go. Here.
Are you only dealing with 2 elements at the moment?
I'm sorry?
Are you only dealing with 2 elements?
No, we're doing with more.
Okay.
We'll do some with more than 2 atoms, or 2 elements as well. And so this one, which one do you want to put in the center? Phosphorus or chlorine? Phosphorus. Less electron. And chlorine, like the other halogens, likes to just form 1 bond. But how many valence electrons does phosphorus have? What group is it in?
5.
5. So it has 5 valence electrons. Chlorine is in group 7, and so how many does that have? 7. So 4 times 7, 28. And then the +1 charge means we remove an electron or add an electron? Remove. So -1 electron needs to be removed. And so we got 28 plus 5 is 33, -1 is 32 electrons total. All right, then next we build a skeleton. So we'll just put phosphorus in the center, and then we'll bond the chlorines like this. since the chlorines are more electronegative, those get priority for extra electrons. So the chlorines are going to get the priority, and each chlorine is going to want an additional 6 electrons to complete its octet, so that gives it 8. So we need 3 lone pairs on each. Chlorine would be ideal. All right, let's see if we went over the number of electrons that are allowed. So how many electrons do I have in this structure now? So what I'll do is I'll just count this. 2, 4, 6, 8. 8 times 4 is 32 electrons. So this structure has 32 electrons. And so that's good. That's what we're supposed to have. Okay, then what do we check next?
See if it octets.
Yeah, we'll check octets. And so we check octets and then count. How many electrons for chlorine?
8.
8. And so all these are the same. All these have an octet. That's good. Those are 8 electrons. How about phosphorus? Phosphorus also has an octet. And so that's 8 electrons. So this structure looks good. Okay, the next thing we do is we make sure there's an octet, and then we make sure to check the formal charge. So when we look at the formal charge, we count the electrons differently. Okay, here, rather than circling all the electrons around the atom, we're going to split the bonding electrons in half. Let me go red.
So that's 7 electrons, the other one has 4.
Yes, good. What has 7 electrons?
Chlorine.
The chlorine. Yeah. So the chlorine, this chlorine has 7 electrons. Actually, all the chlorines are the same. They all have 7 electrons. Is everybody seeing that?
Sure.
Yes? Okay. And then the phosphorus ends up with 4 electrons.
So last one.
Yeah. So if we look at the contribution of chlorine, chlorine gave 7 electrons. And when we look at the structure, did it get those 7 electrons back?
Yeah.
Yes. And so we say it broke even, you know. And so let's say you pay federal tax, and you pay $100. Well, let's say California pays $100 to the federal government, and then you get back $100 from Washington, D.C. You broke even. But what happened to phosphorus? Phosphorus paid, let's say, $500, but did phosphorus get $500 back? No, phosphorus came out short. If it comes out short, does it get a positive charge or a negative charge?
Negative.
It actually gets a positive charge.
That's why there's the plus and the.
Yeah, that's why there's a plus. Exactly. Because phosphorus must have lost an electron. And so overall, if we want to write the complete structure, this is the way we'd write it. One, we write the lone pairs in here. If you're in organic chemistry, they figure you already know how many lone pairs there are, so you can just look at it and see. But in general chem, we do this. And then we circle the formal charge like this. And so we could either leave it like this, or we could write it like this, where we circle the formal charge. Now, what some people do is they, rather than write it 2 dots like this, they'll write 1 line. It doesn't matter. You could write 3 lines around this, but I usually write the dots, even though it takes a lot of time. Like that. and then write the square brackets around this. And then we sum up all the formal charges, you know, +1, +0, +0, +0, and we get the net charge on this. The net charge, which is shown outside the bracket, is the sum of the formal charges, which are inside the bracket. We can also do oxidation state if we're interested in the redox chemistry of this, but we're not going to do oxidation state for right now because the most critical thing to consider is the
Oxidation state is the delta, right?
no, the delta is what we call bond polarity or polarity. Okay.
And are we done the redox there?
No.
Can you go back over?
Okay, now we're going to have three elements here, but with three atoms. We're going to have NOCl. So for NOCl, let's total up the valence electrons. Nitrogen is 5 electrons, 5 valence electrons, group 5. Oxygen is 6, and chlorine is 7. So 5, 6, 7, what does that add up to? 18 electrons? All right, now, what are we going to throw in the center? Should we put, oxygen is kind of natural, I mean, because it often is in the center, like in the center of water, we have an oxygen. However, according to our rule, and of course rules are broken all the time, we shouldn't put chlorine. We should put the nitrogen because
It's the least amount, right?
least electronegative. Chlorine doesn't like to be in the center, although it could. But we could throw, I don't know, oxygen or nitrogen. If it came down to oxygen versus nitrogen, I'm not sure which one we'll throw in the center.
It's just nitrogen.
So if we use nitrogen in the center, and then we're going to put an oxygen on one end and a chlorine on the other end. Or we'll put an oxygen in the center and then put nitrogen on one end and a chlorine on the other end. You know, since a rule is not a law. And then if I'm going to complete the octet, who would go first? Which of these three elements or atoms is the most electronegative? You'd think chlorine, but it's not. It is oxygen. Both chlorine and oxygen are next to fluorine the most, but oxygen wins because it's smaller. They're about the same numerically, but we're going to do oxygen first, and then the chlorine. Okay, then let's figure out how many electrons did we use. 16. So this is 16 electrons. We have 2 electrons left over. What should I do with those 2 electrons that are left over? Yeah, let's throw them on nitrogen. Okay, so now I'm at 18 electrons, so that checks out. All right, am I done? Yeah, I have a problem. I have the problem with oxygen looks fine, right? Because that has an octet. So does chlorine. Chlorine looks good.
Do a double bond on oxygen.
Yeah, I need to do a double bond. But nitrogen doesn't. So we have an octet here, 8 electrons. We have an octet here, 8 electrons. But here, how many electrons do I have? 6. So I'll need an additional 2 electrons. So I need to form one more bond. And so what I'm going to do is let's take them. We're either going to take them from oxygen or chlorine.
Oxygen.
We're going to take them from oxygen because oxygen likes to form 2 bonds. We could take them from chlorine.
doesn't like it there.
Yeah, chlorine doesn't like to form more than two bonds. But let's go both paths, and then we can see. If we take the electrons from oxygen, then that leaves only 2 lone pairs on oxygen left over. And then nitrogen will look like this, and then chlorine looks like this. If, on the other hand, we decide to take them from chlorine, then oxygen looks like this, and then nitrogen like this, and chlorine like this. Now, chlorine's only going to have 2 lone pairs. And we look at the octet rule, and this is good because oxygen has an octet, nitrogen has an octet, and chlorine has an octet. But if we look at this right structure, look at oxygen. Does oxygen still have an octet?
Yeah.
Yeah. And then we look at nitrogen. Does nitrogen have an octet?
Yeah.
Yeah. And then does chlorine have an octet?
Yeah.
Yeah. So both of these structures satisfy the octet rule. And so, which one would you choose?
The one on oxygen.
The double bond on oxygen? And what is your argument for that?
It likes to form a double bond.
Yeah, oxygen does like to form double bonds.
How about by justification by like formal charges, it has more than one variable formal charge?
Yes. We usually use formal charge to argue that the left one's best. And the reason is because the left one, we look at the formal charges, and let's take a look at oxygen, for example. And count the formal charges. So what we're going to do is, again, split the bonding electrons and then count how many oxygen has. How many does oxygen have here?
6.
6. And how many did it contribute?
6.
6. So it broke even. 0. And then how many does nitrogen have?
5.
Nitrogen has 5 electrons. How many did it contribute?
5.
5. So we're even. Chlorine?
7.
And chlorine contributed 7. And so this came out even. So everybody got what they contributed. Okay, let's take a look at this other structure over here. And do the same thing. Okay, this oxygen has how many?
7.
Yeah, 7 electrons.
So it's a minus.
Yeah, it got 7 electrons, but it only contributed 6, so it has an extra electron. An extra electron is an extra negative charge. And so the formal charge on this oxygen is going to be negative, -1. But we don't write the 1, we just write a little negative sign in a circle. Okay, then let's go to the nitrogen,
5.
and it contributed
5. So
5. So this gets a 0. Usually we don't show it. 0 formal charges.
Okay.
And this chlorine has how many?
6.
6.
It's positive.
Yeah, the chlorine ends up with 6 in the structure, but it actually contributed 7. So it lost 1 electron. If it loses 1 electron, it's lost 1 negative charge, which makes this positively charged. And so this is what happens. Oxygen gained an electron at the expense of chlorine. Chlorine lost an electron, oxygen gained that electron. Do you think chlorine's going to be very happy?
No.
Both of them are about tied for electronegativity. So does it make sense? You know, oxygen is stronger, but does it make sense that chlorine's going to be able to do that? No. So we call this unstable. This is less stable because that means there was a separation charge. Chlorine lost, oxygen gained. Both are highly electronegative. Electronegative is En. Whereas over here, everybody broke even. Do you see that? And so this is going to be more stable. And so we say that this is the preferred structure here.
Is there a limit to how many elements can be in a formula? Or are you just
No.
gonna?
No, any. Note the formula. Does the formula tell you which one's in the center? When you look at the formula, it looks as if the oxygen's in the center. The formula can have zero relationship with the structure. Just be aware of that. Even though they show the oxygen in the center here, that doesn't mean oxygen is going to be in the center. You know, the correct formula for this is not oxygen in the center. The correct formula for this is nitrogen in the center. Otherwise, the formal charge comes out kind of high. So this would be the structure of that. All right, let's take a break here, and then we'll start up after the break. So I'm looking at our lab, experiment 8. This will start next week. And so we're going to do this one here next. NO2 minus. So nitrogen has how many? And then we have 2 oxygens. And then a -1 charge. A -1 charge means we add or remove? We add. And so this will be +1 electron. So it's 12, 17, 18 electrons here. All right. In this case, what do you want to put in the center, nitrogen or oxygen?
Nitrogen.
Probably nitrogen. We'll throw nitrogen in the center again. Based on the last problem we did in the rule here. And then we complete the octets. To the terminal atoms, and that brings us to how many electrons now? 2, 4, 6, 8, 10, 12, 14, 16 electrons. 16 electrons, we have 18 electrons, so that means we have 2 extra electrons. Where should we put the 2 extra electrons? Yeah. So if we end up with extra electrons, the order goes first the terminal, that is the outside atoms, and then the inside. And so in this case we did. However, we're still short. Do you see nitrogen? Does it have an octet or not? No, nitrogen does not have an octet. Oxygen's okay with the octet, so maybe I should just keep doing it the way we've been doing it. That looks good. This looks good. However, this does not look good. And so one way we can do it is by converting a lone pair into a bonding pair. And so let's go ahead and do that. But we have a choice. Which oxygen needs to make the sacrifice? 1 or 2? 2, because which oxygen will make the sacrifice for the lone pair? Well, one of them has to. So it's kind of if one of them has to, then they're both the same, right? And so if one, let's say one donates a lone pair, it's going to be left with two bonding pairs and 2 lone pairs. And the other oxygen keeps everything. That's 1. But this is kind of like a flip of the coin, right? It could be either 1 or 2. When we have this situation, then the other possibility is this. And so we end up with 2 possibilities. Is one of these better than the other? Well, they look the same, don't they?
Yes, sir.
Yeah. They look the same. And so we end up with these 2 forms. Let's take a look at the formal charges, because the formal charges, that's what we do next. If we look at the formal charge on this oxygen, what is it?
6.
Yeah, this has 6 electrons. And it donated 6. 0. This nitrogen?
5.
0. This oxygen?
7.
7. And it contributed 6. So this one ends up with an extra electron, which gives it what formal charge? Minus. So the extra electron went on this oxygen over here. Okay, if we look at this, do you see the symmetry here?
Yes.
This one is going to be negative. The other 2 are 0. And so we either put the extra electron on the right oxygen, or we put the extra electron on the left oxygen. Is one more stable than the other? No, it doesn't matter. They're both the same. And so we call these resonant structures. And so we had the choice. And the choice was either the left sacrifices the lone pair into a bonding pair, or converts, which we end up with this structure, or the right one sacrifices. In which we end up with this structure. And to show that these are resonance structures, we do this. We draw the we don't do it that way, sorry. We don't do it like this. We don't draw 2 arrows. We draw 1 arrow. We draw 1 arrow with 2 heads. This is called the double-headed arrow, and double-headed arrows is to signify that we have resonance structures, that we have this choice, and these are 2 equivalent. And so what some people try to envision for resonance structures is it's just resonating back and forth. The electrons are resonating back and forth, but it doesn't resonate. And so even though these are called resonance structures, there's no resonance here. which is odd. No resonance. Resonance would be this kind of back and forth oscillation, but there's no back and forth oscillation. No back and forth oscillation between the structures. We can interconvert between resonance forms by just moving the electrons around. So, for example, if I take this lone pair and bring it into the bond, that makes more than lock it around nitrogen, which we can't have. So that's going to kick out this bonding pair and make it a lone pair. So lone pair converted to a bonding pair converts to a lone pair, and then we switch to this structure. Likewise, to go backwards here, we can take this lone pair and make it a bonding pair, which kicks out one of these bonding pairs and makes it a lone pair. And so we can kind of visualize it going back and forth by just rearranging the electrons, but it doesn't. The actual structure, this is another problem with valence bond theory. What was the first problem that we encountered with the valence bond theory earlier today?
The oxygen.
It was oxygen. And so this is best described using MO theory. It turns out that both the bonds are the same. Do you know what's shorter, what's longer? It turns out double bonds are actually shorter and stronger than single bonds. Like double bonds are not quite twice as strong, but like on that order. And so they're shorter. And so when people think about this resonating, it goes double, single, double, single. And this is single, double, single, double. And so it's kind of doing that. But it turns out that both these bonds are exactly the same. And so experiment shows that both bonds are exactly the same. And so how does that? The experiment shows both bonds are actually the same. So what we end up with is a hybrid structure. A hybrid is just a mix of the two structures. And the hybrid structure is going to look like this. You're not going to have to draw hybrid structures. It looks something like this, where we don't have a double and a single. What we have is a 1.5 bond. This is called a 1.5. That's a 1.5 bond. So they're 1.5 bonds rather than a single and a double. 2 1.5 bonds is equivalent to that. The hybrid structure, this naturally comes out from MO theory. And so we do this with some kind of hybrid structure. If we use MO theory will yield something that looks like this hybrid right off. MO stands for molecular orbital theory.
So MO theory is the reason for hybrid structure?
No. Yeah. Yes and no. Experimental data is a reason. The Lewis structures just didn't agree with experimental data.
Hybrid structure is an MO theory, but it's not a...
No, hybrid structure is not MO theory. Hybrid is from valence bond. MO gives an equivalent to the hybrid structure. Not exactly equivalent. MO is much more detailed and much more informative. But what we do is we're not going to worry about the hybrid structure. We're just going to we just want to draw all the Lewis structures available. And so the answer for this particular question will be these two structures here. And so we say two resonance forms in this particular case. There are two, sometimes we have more, two resonance forms. And so we draw the two resonance forms, like so. Okay, we're going to do this one next. Okay, another rule. Acidic hydrogens are bonded to the most electronegative elements. Most electronegative atoms. And so this appears to be bonded to nitrogen, but it isn't. That means hydrogen is not bonded to nitrogen. That means hydrogen has to be bonded to oxygen, because which one is more electronegative, nitrogen or oxygen? Oxygen. So we're going to bond the hydrogen to the oxygen. But when you look at the formula, does it look that way? No, it doesn't look that way. So if I were to give this on exam 3, maybe a bunch of people will bond the hydrogen to the nitrogen.
Will we given the electronegativity scale or on the exam?
You don't really need it. You just need to know the relative order. Like, it increases, if you do need individual electronegativities, they'll give it to you. And so when we draw the structure for this, I might try to put nitrogen in the center like this, and then two oxygens. This, again, would turn out to be wrong here. Instead, what I'll do is I'll put maybe hydrogen to the oxygen, and then the oxygen to the nitrogen, and the nitrogen to another oxygen. This looks like a better starting point for this.
Do we always go like across, or do we go like up and down?
We can go up and down. It doesn't really matter how you want to do it. And so this is just this rule for the skeleton. And so hydrogen has how many valence electrons? Nitrogen?
5.
And then we have two oxygens at 6 each. It's 12 plus 6 is 18 electrons. How many have we used for this structure over here?
6.
Yeah, 2, 4, 6. And then if I'm going to divide up the electrons, who gets them first? Oxygen. And which oxygen, the middle one or the end one? End one. And then the middle one. And then nitrogen. But are we going to have enough for nitrogen? Let's count how many we've used so far. 2, 4, 6, 8, 10, 12, 14, 16. We do. We have 2 more electrons left. Those 2 more electrons left are going to go on nitrogen.
You go in order of electronegativity, right? Distributing the electrons.
Yes, pretty much. Okay, but do you already see the problem?
Yep.
What is the problem?
Hydrogen. Not hydrogen.
Hydrogen is okay because we only need a duet on hydrogen. The first shell.
Octet.
This oxygen is good. 8 electrons. How about this nitrogen?
6.
No, this nitrogen is not good. This oxygen
That's good.
is good. 8. So now we have two choices. Either this, this is called a bridging oxygen, can donate, or we could have a terminal oxygen donate. Since both are oxygens, we should consider both scenarios. Let's say the bridging oxygen here donates. And so one of the lone pairs gets converted into a bond. And now let's check the octet rule here. Hydrogen still has a duet, that's good. Oxygen has an octet. And so even though this oxygen donated, it still has an octet. But now nitrogen has an octet. And this oxygen over here has an octet.
No, it's the formal charge.
Yeah. It's the formal charge is going to be all screwed up. And this is what gives another rule. Another rule is oxygen likes to form two bonds. Those two bonds could either be two single bonds or it could be one double bond. But in this case I have a single bond and a double bond, so that's equivalent to 3 bonds. 3 bonds on oxygen turns out to be okay, but it screws up its formal charge. Because what is the formal charge? Well, let's take a look. On hydrogen, what is its formal charge?
1.
Well, it has 1 electron. And how many did it donate? 1, so we'd say 0. Oxygen?
It's got 5 now.
Yeah, oxygen has 5 electrons now, but it donated 6. So it came out 1 short, positive. And then this nitrogen, I forgot the lone pair. On the nitrogen and oxygen over here. So the nitrogen has how many?
5.
And nitrogen donated 5, so it's even. This oxygen?
4 charge minus 1.
Yeah, 7 electrons. It donated 6. It comes out with an extra electron. It gets negative. So the way we imagine this structure is there's a tug of war between 2 oxygens. So oxygen versus oxygen. The right oxygen won, the left oxygen lost. Does that seem like a stable scenario? No. Even though the other oxygen has that hydrogen attached to it, we wouldn't expect this to be very stable. Let's go to option 2. Here, next. And we end up with this structure. Does everybody end up with an octet?
Everybody except for hydrogen should do that.
Yeah. And so that's good. We still have 2 on this. Still have 8 here, 8 here, and 8 here. And so octet and duet rule is good. That checks out. So both these structures have an octet. Let's take a look at the formal charges on the second structure here.
All zero.
Yeah. That's correct. The formal charges are all zero. It's 1 electron, that's 0. This is 6 electrons. Comes out to 5 electrons. And this comes out to 6 electrons. So all the formal charges are 0. Normally we don't show 0 formal charges, so I'm not going to bother drawing the zeros and circling them. But as far as like stability, you'd expect the right structure to be a lot more stable because we don't have to have this unfair tug of war. 2 oxygens competing for an electron. They should be comparable in electronegativity. In fact, they should have the same electronegativity according to the Pauling's electronegativity rules. According to others, they're slightly different because of their bonding arrangement is different. But these we would not call resonance forms. Because one, they're not equal. We can have unequal, but they got to be close. These are totally different in energy, and so not resonance. There's one clear winner here, and that clear winner is the right one. Versus in the previous example, was there a clear winner there? No, in the previous example, those were the same energy. In this one, they're totally different energies, and therefore there should be only one structure for this, and that one structure is going to look like this. There's going to be H. Just to redraw it to clear it up. It's like that.
Hydrogen on the other side.
Sure. But that wouldn't be resonance either. And so if I bond the hydrogen on the other side, that is, I flip this molecule around, this is not resonance either. Not resonance. For resonance, we need the atoms to not move. Only the electrons move. For resonance structures, the atoms cannot move. This structure is fine. But the way I generate this bottom structure is I have to take this one and then flip it 180. If I take this one and flip it 180, I end up with this. So what we say is that these two structures are the same by flipping it 180. But you might say the same thing in the previous example. In the previous example, if I take this structure and flip it 180, then what do I end up with? This one. And that's perfectly valid, but the situation is here. When we look at the original, there were 2 options, the left and the right. And so we had 2 choices. In the second example, we only had 1 choice here. We're going to just generate this structure. The only way we could generate the other structure is by moving the atoms. We don't move the atoms. We keep the atoms in position and look at how many choices we have for the electron. So for resonance, never move the atom. Never move atoms in resonance. Let's do another one that's comparable to this. Why don't you try this one for me? We're we're going to try HCO3 minus. So give that one a go. And what I want you to do is figure out the Lewis structure and then any resonance form. Sometimes there's no resonance forms. Sometimes there's resonance forms. So take a look at this and then see. Did I forget to record? Maybe. Forgot to record. But if I forgot to record, we did this structure and this structure after the break. Oxygen-oxygen single bonds are unstable. These are called peroxide bonds. And peroxide. I'm sorry?
We discussed this a while ago.
Oh, did we? All right. All right. Just to remind you, peroxide bonds are unstable. Avoid if possible. Sometimes we can't avoid them.
Is that when we usually replace with a double bond instead?
Hmm?
Did we ever get like a single bond?
Yeah, we could replace it with a double bond, but that makes O2. And so it's very rare. That's, yeah. Or ozone is kind of different. But, you know, peroxide and ozone are unstable. Yeah, so those look good. I mean, this would be good. The question was, do we need the brackets? And the answer is, if there's just one negative charge, probably not. But if there are multiple charges, then we want the brackets, because let's say if there are two negative charges, actually this is 0 here, but let's pretend that there are two negative charges and a positive charge, then the net charge would still be -1. And so what I was talking about was, would this qualify as a resonance form? I'll just do it on this up here. So we take an electron off this oxygen here, make it a bonding pair rather than a lone pair. And we end up with a structure like this, which would be negative here, and positive here. And in this case, we would want to do the square brackets and then add them up. -1, -2, +1 gives us a net negative charge. And so it would be there. And so in a case like this, yeah, it makes sense to put the square brackets here. When we just have one charge, you can do it for sure, but you don't have to. But this is not going to be nearly as stable as those two. And so we wouldn't really consider this a resonance form. Not a resonance form. The reason is because it has higher formal charges. That is, more formal charges that we could avoid with the other structures. All right, so that's good for that particular one. Let's look at some more to try to get volume going here. This one's going to be a bit tricky. Um, you know, we'll try this one. This is not an ion. This is just a neutral molecule. Give this one a go as well. There's one thing that kind of looks bad here. Can you tell what it is? How about the octet? Does the octet look good for all these? Yeah. Octet looks good, but what kind of looks bad is this relatively high formal charge. +2 is a fairly high formal charge. But this is correct. We would end up with 3 resonance forms because which of the 3? You know, there are 3 equivalent oxygens, and we could form a double bond with any of those. But you'd say, well, aren't they all the same? You just rotate it. No, they aren't, because these are 3 possible ways we could distribute the electron: to the left, to the right, or the one down at the bottom for the double bond. So that's correct. There should be 3 resonance forms for this. This structure here, there are 2 problems with this structure. 1, 2 peroxide bonds, and 2, a very small ring. When you have rings like this with peroxide bonds, those are potentially explosive chemicals. You know, there are people who want to make those because the rings turn out to be strained because the atoms are, at least the bonds are kind of kinked here at a 90-degree angle, or sometimes a 60-degree angle, which makes it heavily strained. So we wouldn't do something like this. This is much better here.
So Calvin made a bomb.
A potential bomb, you know, we don't know. Could be very difficult to actually make in the lab, you know.
You're gonna make a bomb?
No, not.
Maybe if you majored in chemistry.
Well, you know, I was listening to this YouTube video coming to school this morning. You know, the people have proposed using little nuclear bombs for jet propulsion, and so they're going to have like little mini explosions, and then they could not jet but rocket, you know, and then send a rocket out to space. But would you want little mini nuclear explosions and sending a rocket into space? You wouldn't, because of all the nuclear waste, you know, radioactive waste. You wouldn't want that.
Sounds kind of cool.
Yeah, it does sound kind of cool, but there's one that sounds much cooler. Rather than using a fission reaction, which has a lot of radioactive daughter products, they're thinking about using a fusion reactor to do that. And so, problem with a fusion reactor is a lot of fusion reactors will emit neutrons, but they figured out a way to do a fusion reaction without emitting neutrons. So they get a proton to combine with a helium, I think, and that creates a boron, and the boron breaks into 2 heliums. And so the product of this fusion reaction is helium, and it's neutron free. I forgot what they call it when there's no neutrons there. Because the neutrons cause a lot of damage. So that sounds pretty cool. So I guess SpaceX is going to launch that with a fusion. It's a little nuclear reactor, but it's a different kind of nuclear reactor in the future. And so one of the things here is this. There are 2 choices. One with the octet and high formal charge. So octet is good, but high formal charge is not so great. And so let's pick one of the resonance forms here. I'm not going to draw all of them, but if we pick one of the resonance forms, Now I'll try to draw the single bonds a little bit longer, but it turns out all the bonds are the same. So all the bonds are the same length because it's not it's not this one, or this one. It's a hybrid of the three. That's the real structure for that. But let's just pick one of the resonance forms, this one here. And so the high formal charge is +2. What we can do is, if it's possible to get an expanded octet, an expanded octet would be to reduce formal charge. And so an example of an expanded octet to reduce formal charge would be like say, let's make another double bond. Tell me what the formal charge is on this structure. There'd be resonance forms for this as well, just like there are resonance forms for this, but we're just going to look at one. How many resonance forms, without drawing them, how many resonance forms can I draw for this? 3. What are they? There's left, right,
Right bottom.
yeah, right bottom and left bottom. Those would be the 3 resonance forms that we could draw for this. But the formal charges have been reduced. What are the formal charges now?
Plus and minus.
Yeah.
Plus on the sulfur and minus on the bottom.
Yeah, plus on this sulfur, minus on this bottom. We can further expand. This has an expanded octet because now sulfur has how many electrons around it? And so, for the octet, I'm saying. Yeah, this is not good because we went from 8 electrons over here to 10 electrons, so we had to expand it. Where do those 2 extra electrons go? Because if we fill the shell, sulfur's in the 3rd shell, so if we fill the 3rd shell, where did the 2 extra electrons go? You'd think it goes in the 4s, but it doesn't. It would go into the 3d, so it's going to bypass the 4s. And that's kind of weird, but the reason it bypasses is because they're all the same 3. The 3rd shell, 3p, we go up to 3d. All the little things to worry about. We can further expand this. Yes. If we go with 3 double bonds, like that. How many resonance forms for this can I draw? There's only one. Both of these will have 2 more. This is only 1. But what are the formal charges in this structure here?
0.
All 0.
With the octet is screwed up.
Yeah, the octet gets screwed up. Oh, yeah, right. Oxygens are fine. It's just the sulfur only. And the sulfur here is going to have how many? 12. And so I have 4 extra electrons. Where do those 4 extra electrons go? They're going to go into the D. And so here, the 2 extra electrons, 2 extra electrons will go into the 3D, into 3D. And here I'm going to have 4 extra electrons. Will go into the 3D. In the next shell, the 4th shell. So now we have a difficult comparison. On the one hand, creating higher charges requires energy. So, and not only that, the charge separation requires energy. And so what requires more energy? Does maintaining the high formal charge require more energy? Producing and maintaining the high formal charge? Or does expanding the octet, promoting electrons in the next shell require more energy? Because what we want to do in this is we want to maximize the bonds. The bonds mean stability. And so the more bonds we can form, the better. And so if that's the case, this forms a lot of bonds. 2, 4, 6 bonds, three double bonds. But over here, we only have 4 bonds. However, when we have separation of charge, we also have Coulombic attraction. And the Coulombic attraction of opposite charge is called an ionic bond. So we have covalent and ionic bonding occurring here. And so we got to weigh all these things together. And so when you look at the structure of SO3 on the internet, let's see what they do for the structure for SO3. This is wrong. How do they get that structure? This is wrong. Can you tell me what's wrong with this structure? Automatically, I see that structure is impossible. Why? Because of the number of electrons. When I count the electrons here, I get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. How many electrons does SO3 have? 24. So automatically, if somebody wrote this on a test, boom, that's wrong. Totally wrong, because there's only 24 electrons. Where are those 2 extra electrons coming from? I don't know. This is why you got to watch out, because the stuff on the internet doesn't have to be scrutinized. So here's a case where they expanded the octet and minimized the formal charge. Here's a case where they're looking at different scenarios. This first structure is bad. What's bad about this first structure?
Their formal charge is extreme.
Yeah, but even worse. The first thing we always look for is... No. Well, we do electron count first, but the first thing I look for in a structure is... If I'm grading this, I'll tell you the first thing I look for. The first thing I look for is octet. Does the first structure here even have an octet? No. If somebody wrote this structure, that's a lot of minus. A lot of red ink. What about this one? This one's okay because this one has an octet, but they really screwed up because what should be the total charge on this? After I look for octet, this has an octet on all of them, but then the next thing I look for is the formal charge. Yeah, this whole thing should be -4. You see -1, -1, -2, -4. Is that correct? No. All these structures are wrong, unfortunately. Let's see. What are they doing here? What they're doing is they're doing some non-equivalent resonance forms. But we don't know exactly what's going on with the energy. And so this is with an octet. So the top 3 are with octet. The middle 3 are with partially expanded octet. And the bottom one is fully expanded octet. And it's kind of a trade-off, do you expand the octet? That's going to cost energy. Or do you maintain the high formal charge? That's going to cost energy. And so which one is better? So that becomes a more complex. It turns out, I should probably tell you that recent theoretical studies have shown this. recent theoretical studies have shown that the octet rule is more like an octet law when it comes to expansion. Recent studies have shown that we shouldn't expand the octet. You know, I told you, where do the extra electrons go? They go into the d orbitals. But they did some quantum mechanical studies, and they found that there's very little or zero electron density in the d orbitals. So that implies these first three structures are the best here. That is, we got to live with a high formal charge because expanding the octet is just too costly in terms of energy. Does that make sense? And so what do you do? Well, I don't want to have you learn expanding an octet and then, well, maybe we'll do it as a historical perspective. Maybe we'll just expand the octet. When we have a chance, expand the octet and lower the formal charge. So you have two choices: expand the octet, lower the formal charge, or just leave the octet and live with the formal charges. I'll tell you what to do on a case-by-case scenario, but this one's hard because of that. Since this expanded octet idea has been around for a long time, when we do look online, most everything we see is expanded octet. So let's take a quick survey of the images for SO3, and do you see what they've done? The great proportion of them have. Chemistry is an evolving field like all science, you know. So as better and better data comes out, then we can refine our understanding of these things. But you look at most of these structures here, and most of them have 3 double bonds. Mm-hmm.
When it has the double bond, it looks like a fidget spinner.
Yeah, it does. It does. And in fact, it have the exact same shape as the fidget spinner here. All right, so that's a tough one. Tough call. How about this one? Let's see if this one's going to be as complex as the last one or not. Complex meaning if we start factoring expanding octets. We only factor in expanding octets if it's a big atom and it's the 3rd shell or higher. So 3rd shell, 4th shell, 5th shell, okay, but 2nd shell, 1st shell are never going to expand the octet. They're very small atoms. We never expand those. Or would even consider it. Now, you know, with the recent data, maybe we shouldn't consider expanding octet at all. And so this is good here.
On the exam?
I don't know. This one is the simplest amino acid, glycine.
Simplest?
The simplest of the amino acids.
Check the data, it's not April 1st, May 1st, no joke.
Is it an amino acid?
Yeah, glycine.
What's the most complicated one?
There are more complicated ones for sure,
Professor,
but I guess it depends on who you talk to. Uh-huh.
like you said, just going off of your previous statement, the formation of the formula is nothing to do with the structure. So where the hydrogens and the oxygens are placed,
Right. Do you see this formula is written quite a bit different? They didn't combine all the hydrogens. And they didn't combine all the carbons. They did combine all the oxygens. And so this is what we call a condensed structural formula. When you see a condensed structural formula like that, it's giving you clues to how things are bonded. Yeah, so there are definitely clues on how it's bonded here. Well, let me give you a hint here. So for example, are these hydrogens bonded in between the nitrogen and the carbon? No, these hydrogens actually belong just to that nitrogen. And that means these hydrogens must belong to which carbon?
the first.
Yeah, the first one. And so there's certain clues in the condensed structural formula. So give this one a shot here.